Hello, everyone. I'm Debalina. I'm from University of Tennessee. My research interest is 3D printed concrete, high performance concrete, and alternate binder. So this is part of my research, and I'm really glad to be here and present in front of you a part of this. And today I'll be discussing about the effect of interlayer time-lapse and workability retention on 3D printed concrete. This is still a research in progress. So can you? Okay. So we are working on it. And so when we are talking about 3D printing of concrete, what most of the time we mean is extrusion-based additive manufacturing process where we put one mortar filament on top of one mortar filament to gradually build an object, a wall or something, without relying completely or like minimum support from the formwork. But what does this mean from a material perspective? How is it different from the cast concrete? The main difference we get from printed concrete is that it has this interlayers that creates anisotropy. And we do not get to see that in cast concrete. So what is anisotropy is basically when a material reacts differently based on how you're loaded, based on the loading direction. So when you are casting a concrete wall or slab, you do not want these kind of joints or this kind of anisotropy in your cast concrete, but that is not avoidable in printed concrete. So that is, these interlayer joints are one of the big reasons why we cannot use the standard testing method, standard evaluation technique for that we use for cast concrete, and we cannot use them for printed concrete materials. And my research focus is on the two main knowledge gaps on this area. And the first research objective is to study the effect of interlayer time-lapse on the mechanical properties of printed concrete, which includes fracture property. I also did other studies on compressive strength, flexural strength, and I used cast concrete to compare the test results. And the second thing is I wanted to investigate how these properties correlate with the concrete workability retention. So I used a dry mortar mix developed by Quikrete, although the setting time was 5 hours according to ASTM 403, but the workability started declining after 30 minutes. And I used this print material to print the concrete using a 2x4 nozzle. And I chose interlayer time lapse of 10 minutes, 15 minutes, 30 minutes, and 60 minutes for 4 batches. And these printed concrete were later cut into small pieces to test compressive strength, flexural strength, and compactness index. So before we get into how the mechanical properties are, let's see how the concrete matrix looks like for printed concrete and cast concrete. So I used SEM to look at the specimens, and I took this specimen images to image J to quantify the area fraction of the pores and the aspect ratio of the pores. So if you look at these pictures, you can see, and also if you look at the quantification of the pore areas, you can see that the area fraction of printed concrete and the aspect ratio of the pores, they increased compared to the cast concrete. So we have more pores and we have more elongated pores. So having elongated pores and more pores may be bad for the concrete itself, because elongated pores means you have higher stress concentration at the corner of the pores. So now compressive strength. I use 2x2 cubes for compressive strength. And for printed concrete, I used two different loading directions. One is parallel to the interlayer surface, and the second is perpendicular to the interlayer surface. And for both of these, I used a bi-layer specimen, which means we have only two layers in this. And if you see here, the compressive strength of the print material is lower than the cast concrete. And another interesting fact I saw in the parallel loaded sample is that the specimen broke in the interlayer before the whole specimen fails. So if you look at that, the stress at which the layers separate is significantly lower than the failure load, and it fails at the interlayer, and this stress can indirectly indicate the tensile stress at the interlayer. So now the flexural strength. Also for the flexural strength, I used parallel loaded specimen and perpendicularly loaded specimen for printed concrete. For parallelly loaded specimen, which is logically, it has way lower strength compared to printed concrete, but that's not really the case for the perpendicularly loaded specimen. We also saw that the crack pattern in the perpendicularly loaded specimen has a very distinct trend. This is cast concrete. So if the interlayer time-lapse increase, which is this from here, we saw that the crack pattern, the crack goes up through the bottom layer, goes through the interlayer, and then again goes up. And this part increases with the interlayer time-lapse. And actually, in the literature, I saw that other anisotropic concrete, like ASR-affected concrete, also shows this kind of tensile crack propagation influenced by the pre-existing horizontal cracks. Now, for the fracture properties, I used compact tension test using, again, bilayer concrete specimen. One of the reasons was that for large specimen with multiple layers, those are prone to interlayer defects, so it can break even before the fracture, even before the testing, during sample preparation, and even during the testing, it might not break where you want it to break. So that's why we chose compact tension test. We had the interlayer aligned to the notch in the middle, and I applied tensile strength, tension on these two holes. So for this one, I plotted load versus the crack mouth opening displacement, and you can see that from the cast concrete to printed concrete with higher time lapse, the peak load gradually decreases, and the failure pattern changes with the time lapse. Now, one of the major fracture parameters that depends on the peak load of the concrete, peak load of the specimen is fracture toughness for linearly elastic materials. So that obviously gradually decreases, but for the 30-minute samples and for the 60-minute samples, the concrete does not act like a linear elastic materials. So these two data points are here just for the visual purpose. It is not, we need more research to find out the accurate fracture toughness of these two data points. But when we look at the fracture energy is basically the amount of load needed to break a specimen in two pieces for per unit area. So basically, all the area under the load versus CMOD plot normalized by the fracture surface. And that's what we have plot here. And you can see that fracture energy from cast concrete to printed concrete is significantly different. It is lower, so we need way less energy to crack through a fracture, a printed concrete, even though the peak load is not that much different. So the main takeaways from my research is that printing process does affect the pore structure and it can impact the mechanical performance. The second is how the time gap between two printed layers affect the concrete properties changes with the alignment of the loading direction, and longer time gap does not always mean that low strength, does not mean that it will have low strength. But if the loading direction is parallel to the stem, the loading direction is parallel to the interlayer, that strength is more affected by the time gap, which is logical, but it does not always affect in the same way. Like we saw in the flexural strength, it did not affect but for the compressive strength with parallel direction, the interlayer split. So it affects differently. Although the fracture property, we saw that peak load does not, it reduces gradually, but for fracture energy, it does not really, the fracture behavior does not change with the Interlayer time-lapse. We had almost similar fracture energy for all the printed concrete. And all the properties that are affected by Interlayer time-lapse, we saw that the bonding strength declines further for 30 and 60 minutes. We saw that for compressive strength, where parallel to the loading direction. We saw that for flexural strength parallel to the loading direction. And we saw that for fracture toughness or the fracture peak load. And this thing, the 30 minutes timeline coincides with the workability retention trend of the mix design. We saw in one of the first slides that workability starts to reduce at 30 minutes. So we can say that the workability retention trend can be used to predict the optimal time span of 3D printing. So if we test the workability retention trend, it will give us a timeline within which we should be printing the concrete without bothering about, oh, this is gonna have a bad effect on concrete properties. So that's my research in a nutshell. If you have any questions, I'll be glad to answer that. And thank you for your attention and time.